Okay, hello. I sound like RuPaul. Hello. Anyway, I really hope that you watch this video now just for that. Anyway, okay, so we're moving from one suite of sort of geoengineering techniques, the solar radiation management, now to the other, what I would call like the other sort of category of geoengineering techniques or proposals, which is carbon removal techniques or carbon capture or carbon sequestration. And there are three dominant sort of methods to this like category of techniques. We have geologic sequestration, so carbon capture, carbon storage mechanically using technology. We have terrestrial sequestration, which is basically planting more trees, right? Aforestation. And then we have ocean fertilization, which is basically stimulating the oceans with various minerals and elements and other things to essentially fertilize the ocean so that it can capture more carbon. Before we get to all of that, I just want to briefly review combustion, like why we care, about carbon capture and storage. So combustion, of course, is the process by which we burn a hydrocarbon, oil, gas, or coal, which produces a bunch of waste products, carbon dioxide and water vapor, and also a lot of heat. And it's that heat which, there's a video here if you'd like to see that, but it's that heat, the explanation of combustion and the chemical reaction. Sorry, that's what the video is. But the heat, which is what I'm really after, so I'm going to say it another time. The heat, 4 times, there we go. The heat, which is typically in the furnace, boils some water, which is running through a pipe. As the water boils and turns into steam, the steam powers a turbine, which generates electricity, which then is transmitted over transmission lines, and that's how you turn your light switches on and do other various things. Okay, so I froze, of course. Okay, here I am again. It hates me. Okay, we're back. So, of course, burning a hydrocarbon produces a waste product, a byproduct, carbon dioxide. And we know carbon dioxide is a disaster for the climate and for the environment and for the planet in general. So, just looking at the US sources of carbon dioxide, in 2015, there were 5.2 million metric tons emitted. And fairly evenly distributed between coal, natural gas, and petroleum, maybe slightly more on the petroleum side of things, although you can see that by industry they're not even. So, for example, the transportation industry relies primarily on petroleum. The industrial industry is kind of evenly split, although it relies pretty heavily on natural gas. Same with electric power generation relies heavily on coal. These numbers are changing. This was 6 years ago. Our natural gas production in this country has increased exponentially. If you take my environmental disasters course, we talk about fracking and the extraction of natural gas from the earth. And so that number is increasing in lieu of the coal number, which continues to decrease. They're kind of replacing each other. And we're not going to do this because we already did this earlier in the semester, and there's no need to repeat it. But to remind you, there are 3 main types of fuel: oil, natural gas, and coal. Coal's been around sort of the longest. Oil was discovered in the early 1900s and really had a boomlet in the 60s, 70s, and 80s. And now the world is really embracing, for better or worse, mostly for worse, actually all for worse, natural gas as a fuel. So this all matters, of course, because as we talked about last week, we're putting all this carbon into the atmosphere, and as that carbon dioxide accumulates in the atmosphere, we're at, let's see if I can uncover the number here. Oh, I didn't save the number, but we're at about 415 to 420 parts per million concentration of carbon dioxide observed at Mauna Loa. And this record, going back to 1958, shows that the concentration of carbon dioxide is steadily increasing, if not accelerating, and this of course is causing all kinds of problems. The first and foremost, sort of most pressing problem, of course, is climate change, as we've been talking about. No need to redo all of that. We had the carbon budget and the carbon cycle lecture last week, and so draw on that for kind of a segue to this discussion today. So here's the thing. Here's the idea. Folks who advocate for geoengineering have proposed three carbon capture proposals, right? As I mentioned, there's the direct capture, right, and storage of carbon dioxide through mechanical or industrial means, which I'll spend quite a bit of time talking about. There's also afforestation, which is planting vast forests, and then there's ocean fertilization. These arrows represent the solar radiation management proposals, which we've already spent many weeks talking about. So we're just going to talk about these three today, the carbon capture proposals. So let's start with geologic capture. Geologic capture is the process of capturing carbon dioxide, which of course is a waste product of combustion, and injecting it into the ground before it is emitted into the atmosphere. Okay? And the idea is that once it's injected and stored in the ground, it will not accumulate in the atmosphere and will essentially reaccumulate back underground. And so it's quite a lengthy process, quite an involved process. You have your power plant, you have your attached to the flue, right, which is sort of the exhaust pipe where the carbon dioxide waste is emitted out into the atmosphere. In this, you basically hook up let's call it a gadget, a fairly large machine, which separates the carbon dioxide from the rest of the gas. Now, the reason we're putting this directly on the flue is because that's where the concentration of carbon dioxide is really high. Remember, in the atmosphere, the concentration, while it is going up, is only about 415 parts per million. And while that's really bad, I don't mean to say only that it's not bad. It's only that, meaning it's only 415 atoms, essentially, or molecules of carbon dioxide per million molecules of atmospheric air. So that's a very complicated and costly process to remove that from the direct air. But if you remove it from where it's being emitted from the exhaust pipe at the power plant, the concentration is a lot higher. And obviously, because the air there is basically just the air that's burning off of the fuel, and so it's much easier to separate the carbon dioxide from the other gases if you attach it right to the flue. Then we have to compress the gas into a sort of a dried out, dehydrated form, and then along the way turn it into like a semi-solid, semi-liquid carbon dioxide, and then inject it via an injection pump into the ground, into an injection well. And we're going to talk about where these wells are located and how we find them and which ones are good, which ones are bad. We'll spend a lot of time talking about that, but I will mention that these wells are far below the surface where presumably they can't escape. The gas can't re-escape back into the atmosphere. It's basically, essentially, the idea is we're putting it back in the ground where it came from. So where are we putting it in the ground, right? So perfect segue. Good job, Mika. So just to, let's see. There's nowhere good to put me. Put myself down here. Okay, so there I am. The most available place to put this geologically captured carbon dioxide is in deep saline formation. So on this graph, that would be 3. And deep saline formations are salty, sort of unusable groundwater-y type spaces deep below the Earth's surface, where there are lots of air pockets. It's quite porous, and it's a good candidate for storing this condensed carbon dioxide. Um, Another option of places to store this carbon dioxide is in depleted natural gas and oil reservoirs. So that's what these two rows represent. So you have um, number one here, depleted oil and gas reservoir. So essentially, where you got the gas from, you're putting the waste carbon dioxide right back in the same spot. So it's obviously you're not going to put a natural gas back because you've burned it and you've produced all these waste products. You're essentially just putting this condensed, semi-solidified sort of carbon dioxide material back in there. Another very good potential option for where to store this carbon is in unminable coal seams. So coal seams that are either too difficult to get to or just kind of not ideal, too costly essentially to mine, but we found them, and so in theory you could drill a well down and pretty easily inject the carbon dioxide waste into it. So this map shows the theoretical carbon capture storage potential by country. And I mentioned at the end of last lecture that this is a geoengineering technique that we are actively pursuing, especially here in the United States. And per this graph, you can see why. The United States has probably the largest theoretical carbon dioxide storage capacity of any country in the world, rivaled only really by Russia. And that's because primarily, I think, because the United States and Russia both have very large natural gas reserves, and natural gas reserves typically found in these like sort of deep saline formations. That's where we frack. The hydraulic fracturing is occurring in shale formations and other formations that are also decently ideal candidates for carbon capture. So you can see that this map shows that the carbon capture industry would be dominated by the global north, by Russia, by Canada, and by the United States, although quite a bit of potential in Africa and the Middle East, some of which perhaps is undiscovered. So these numbers are just estimates currently. So let's focus on here in the United States. Where can we capture this carbon? Basically, everywhere on this map is kind of a candidate. So you have these deep saline formations, which I was talking about as sort of the ideal candidates, especially in the West here. You have many potential options out here in the West. But there's also emptied out gas basins and oil basins, and again, these unminable coal seams, which are also reasonably decent candidates for geologic capture. Unfortunately, some of the most ideal candidates and places for carbon capture also come with substantial risk. So here's a map showing the surface hazards risk from tectonic activity, right? And you've got, of course, California and the West Coast along the San Andreas Fault and the Cascadia Subduction Complex. You also have this New Madrid Fault Zone on the border between sort of Missouri, Arkansas, along the Mississippi River, and then some other sort of lower risk areas scattered about. So these moderate to high risk areas also overlap with really good sort of carbon capture and storage potential basins where we could store this stuff. So we do have to keep that in mind. We also have to keep in mind that lots of regions like up here and throughout Texas and in Michigan and along the Appalachians is where there's really intensive hydraulic fracturing, or what we call fracking, occurring. And fracking has increased the potential and the danger of surface hazards. When we say surface hazards, of course, we mean like earthquakes and other tectonic activity. And so you might make a little red bubble here and here and here and here and here due to our fracking activity, which has increased the earthquake risk and therefore makes it a riskier place to put the carbon. Why is it risky? Because if we have an earthquake, right, then all that carbon that we trapped down in those saline formations or in those coal seams or in those emptied out natural gas basins is going to potentially escape back out to the atmosphere. So we don't really want that to happen. We don't want to waste all this money sending carbon down into the earth to then only have an earthquake send it back up into the atmosphere. I'll also say that carbon capture, geologic capture, is very expensive. Here's a chart showing a cost comparison of sort of overnight capital cost and then the levelized cost when you kind of normalize it for everything. It's dollars per megawatt hour. And you can see that the ultra supercritical coal with 90% carbon captured and storage costs about 3 times as much as just an onshore wind mill per megawatt hour. So it's baffling to me why we would continue along this path when we could easily spend less money just building renewable sources of energy. But again, you can see that if we don't include the carbon capture and storage, and we're just looking at this supercritical coal, the cost is about $60. So that's about equivalent to building a new windmill. So in theory, you could say, okay, well, let's just put the carbon capture on a coal power plant that already exists. And then that's about equivalent to the wind and a little less than a solar power plant. And so I can see some arguments here for and against, and I'd love to have that conversation in class with you all. Okay, so make sure that you remember if you have any questions, jot them down and make sure to ask me. Let's move on to aforestation. So aforestation is essentially terrestrial carbon capture. This is when you're planting more trees. And again, trees are really good at fixing carbon. Fixing carbon, essentially removing carbon from the atmosphere. It's fixed through a photosynthetic process where trees convert carbon dioxide in their leaves to sugar. The waste product, of course, is oxygen, which we then breathe as humans. So when trees die, their carbon is decomposed, their branches and their biomass is decomposed, and some of that carbon is transferred into the soil, where it then sometimes stays for really long periods of time. But either way, putting up a tree, right, you're capturing that carbon for at least 50, 100 years, potentially longer, depending on how long it stays in the soil. So it's not as rapid carbon capture, but it's if you plant enough trees, then you'll get a decent amount of carbon capture. So the thing is, with aforestation, you do get quite a bit of carbon uptake. So if we look at this map here, or this chart here from 2005 through 2095, sorry. If we look at just the aforestation bars, that's what the AFF stands for, right? BECCS is carbon capture and storage, and BAU is just business as usual, nothing is happening. You can see that if we do the aforestation, if we take that route, by the end of the century, you could potentially be capturing, about 700 gigatons of carbon dioxide equivalent. And if you add the carbon capture and storage, you get down to 1,000 or more gigatons of carbon dioxide equivalent, which is being taken up, which is a good thing. That's not a bad thing, and it's a good thing to plant trees, I think, on the whole. One issue is that all of those trees, right, also contain nitrogen, which is a limiting nutrient. It's a fertilizer. It's what we use in fertilizer, in fact. So if you're planting all of these trees, they're going to inevitably have nitrogen in their biomass, in their leaves, in their trunks, in their branches. And when they die, that biomass, as it's decomposed, some of that nitrogen is turned into N2O, nitrous oxide, which actually we haven't talked about much, but is a very potent greenhouse gas. And so if you've got more trees, then you have more decomposition, and therefore you have more N2O emissions. So you're offsetting some of the carbon that you're taking up by increasing the amount of nitrous oxide that's being emitted to the atmosphere. So that's a potential issue. That's a potential problem for climate change, that some of the change is being offset by emissions of nitrous oxide. Another problem is that you need land to plant more forests. And so if you are taking up some land to plant forests, that means you're taking away land where you can farm. And according to one study that I have shown here, food prices under an afforestation plan, under an unrestricted afforestation policy, would skyrocket, 500 times higher than they were in 2010. If you only do tropical afforestation, you can mitigate this somewhat, maybe reclaiming some of the land that we deforested in the tropics, especially towards the end of the century, where you've got, maybe just a 50% increase instead of a 500% increase in food prices. So there are ways to think about this, but if we just plant trees willy-nilly, there are a lot of potential problems that could come with that: increased nitrous oxide emissions, food prices skyrocketing, and also, finally, trees are quite dark. They're quite absorptive of solar radiation, and so if you are to plant trees where the land surface was brighter than the resulting forest will be, then you're going to offset some of that carbon you take out by an increase in warming, right? You're going to absorb more solar radiation, you're going to reduce the Earth's albedo, and this is going to offset some of the climate cooling that you're going to initiate from the afforestation process. We're going to skip this and move to, I'll talk about it in class. We're going to move to ocean fertilization. So ocean fertilization is essentially this idea that we dump a bunch of iron into the ocean. Why are we dumping iron into the ocean? Well, let's look at this schematic over here. So if we look at this schematic, most of the Southern Ocean, the ocean that kind of circumnavigates Antarctica, is iron depleted, meaning it needs iron. In order for the plankton, the phytoplankton, to grow more robustly, there needs to be more iron. And so one proposal is that ships could offload iron into the ocean. This iron would stimulate the phytoplankton to increase their photosynthetic capacities, and this would capture carbon dioxide from the atmosphere. The dead plankton, once the plankton have their little life cycle fun, then they'll die and they'll sink, and they'll take that carbon that they took out of the atmosphere with them as they sink, slowly bringing the carbon to deeper and deeper waters where it conceivably would stay for long periods of time, right? So the fantasy here is that plankton populations would rebound to historic levels, reviving fisheries, sequestering vast amounts of carbon. The fear is that iron would lead to a phytoplankton bloom so large that it would deplete deep water oxygen, which would change the whole entire food chain, promote toxic species, and ultimately result in a resurfacing of the carbon dioxide. But let's look at the results of a scientific experiment that were done on ocean fertilization. So this chart is a bit difficult, so I'll try to explain it. Difficult to interpret. So these graphs are showing the amount of carbon dioxide that was measured in the surface ocean after a fertilization experiment. So the fertilization experiment occurs at time 0, right? And this one here is the plot of ocean that was fertilized, and this one here is the plot of ocean that was not fertilized. And so what you can see very clearly is that in the surface water, so this is the surface and this is the deep ocean. So as we go down, this is deeper and deeper. The surface water, the amount of carbon in the surface increases pretty quickly after fertilization. So about 30 days after fertilization, the amount of carbon that's now been added to the surface of the ocean has gone up significantly. You can see this line going up. Same with the next level down. But then as we start to get deeper, it takes a little longer for the carbon to increase, and that's because it takes a little while for this phytoplankton to first live, then die, then sink. So this is as the carbon is sinking, 30 to 40 days later, this depth is now starting to see an increase in carbon. Same as we go deeper and deeper and deeper, right? So you can see that by 30, 40 days, even way down here, the amount of carbon that's been trapped, that's sitting there, is much higher than it was at the beginning of the experiment. So it's a significant increase. So in fact, it does work, but as usual, we have to consider the risks. Oops. We have to consider the risks. And so that's something that I've talked a bit about, right? On the previous page here, this depletion of deep water oxygen. Creating an anoxic environment is really dangerous. We have similar type events called red tides, which often happen along the coastline in like Louisiana and California. And we know these to be pretty problematic and pretty deadly for ocean life. And so if we're going to do this experiment, we need to figure out how to mitigate that, how to not have that happen, but to still have the carbon capturing potential of the iron fertilization. So it's a tricky balance, and I don't really know how we do it, but in theory, this could work. It has been demonstrated with scientific experiments. There are some other methods like direct air capture, which I talked about briefly, and we'll talk about more on the Zoom, and enhanced weathering. And just to kind of give you some schematics about these proposals, direct air capture would basically be like the geologic sequestration, but directly capturing it from the air. Remember, I said that the concentration of carbon dioxide in the air is much smaller than it is coming directly off the exhaust pipes. And so you'll need a pretty fancy machine to do this, probably very expensive, and the technology doesn't really exist for that yet. And same for enhanced weathering. Enhanced weathering is essentially increasing the surface area of exposed silicate rock, right? Silicate rock has a chemical reaction with rainfall, which the rain has carbon dioxide in it, right? And so the silicate rock combines with that carbon in the rain to produce a carbonate which would run off into the ocean and ultimately deposit it into the limestone. So this would be one way that you might capture carbon. There's a lot of problems with it. To do it on an industrial scale would involve extracting and distributing and crushing a ton of rock, and the costs would be astronomical. Here, I'll leave this up here. This project will be due May 12th. Sorry, that's a typo, but we will talk about this. It's been posted to the website. It's been posted to the Google Drive, and so refer to that assignment for the details. Don't refer to the lecture, refer to the assignment. All right, cool. That's all I've got for you, and then we'll talk more about this on Zoom.